Here's an example of 3 charges, and we're going to find the force on one of them due to the other 2. So the 3 charges are arranged on the corners of a rectangle, on 3 corners of a rectangle, and the rectangle has dimensions 40 centimeters along the horizontal and 30 centimeters along the vertical. And the 3 charges are Q1 is negative 25 microcoulombs, Q2 is positive 20 microcoulombs, and Q3 is 50 microcoulombs. And we're going to find the force on this one. To do that, we need to use the principle of superposition. And the principle of superposition says that if we want to find the force on Q3, so we want the force on 3, we need to find the force on 3 because of 1. So I usually write that 1 on 3. So I usually put the source charge first, and then we also need to find the force of 2 on 3. And each of those are vectors, and we can eyeball this really quickly and see that they are not in the same direction. I could draw another. So between Q1, so we know we're going to need this distance. I'm going to call that R13, the distance from 1 to 3. And then we're also going to need, while I'm doing this actually, the force between these 2 is along the lines between them. And since this one's minus and this one's positive, they will attract each other, opposites attract. So the force of 1 on 3 is going to be this direction. And these 2 are like, so they will repel. So the force of 2 on 3 is going to be this direction. So the forces, right now, we can worry about exactly how to write that as a vector equation. We will write that. But right now, for the moment, we can just leave it, leave the arrows. We have to recognize they are in different directions. We're going to need to break each of those forces into components and then add the components. Well, this one nicely is just purely in the y direction, so there's that, makes it slightly easier. But F1 on 3 is definitely in 2 directions. Let's break that up and do each of those 2 pieces separately. So F2 on 3 is slightly easier because it's totally in the y direction, so why don't we start there? So to get F2 on 3, just Coulomb's law. Now it's broken down to where we just have 2 at once. So K, Q2, Q3. On the picture, I didn't label this one. R23 is the notation I'm using, and that is squared. And then R23 hat, meaning the unit vector from Q2 to Q3. Plug all that in. So we have 9 times 10 to the 9th Newton meter squared over Coulomb squared. Both of them are positive. Q2 is 20 times 10 to the minus 6th coulombs. Q3 is 50 times 10 to the minus 6th coulombs. And the R from 2 to 3 is this direction. R2 to 3. This picture, I realize this picture is getting really crowded. Hopefully you can see which thing is which. And that will be the vertical side of the rectangle was the 30 centimeters. To change centimeters to meters, you just move the decimal point 2 places. So that's going to be 0.3 meters. And then the direction of this R vector is and it's the same direction in this case as the force because they're both positive, is in the y hat direction. Some books write that as j hat. So if you're used to seeing a j hat, that's like a j hat. It just means a unit vector in the y direction. I'm actually probably going to, when I write them at the end, I'm probably going to write it as a column vector. Now we just crunch out those numbers. I did choose numbers that work out nicely. 2 times 5, of course, is 10. And then there's an extra couple of zeros. The 0.3 squared is going to give me a 9 squared, so that I'll be able to cancel the 9. If you plug everything in and work it out, it ends up being exactly 100 newtons. And again, that's in the y hat direction. I mentioned we might want to write that. I like column vectors. Whenever I add components, I like to use column vectors. As a column vector, that would be represented like this. All right. If you have a way to, I'll write that over here, and I'll erase that side and calculate F1 on 3. So we just calculated that F2 on 3 vector is equal to nothing in the x direction, and we have 100 newtons in the y direction. And the lower component of the column vector indicates that. And let me erase this, and like I said, I'll calculate F1 on 3. Okay, so F1 on 3 is equal to KQ1 Q3 over R1 3 squared R hat 1 3. K is our 9 times 10 to the 9th Newton meter squared over Coulomb squared. Q1 is our negative 25. I do put the minus sign in, times 10 to the minus 6 coulombs. I'm gonna run out of space. Q3 is 50 times 10 to the minus 3 coulombs, and then divided by the R13 squared. It's squared, which is really nice because I can use the Pythagorean theorem that it's going to be the 0.4 meters squared plus the 0.3 meters squared. It's a 3, 4, 5, right? Triangle I always like the 3, 4, 5s, so that's going to end up being, just that part is going to end up being 0.5 meters squared. Just that part. And then we do need to put in here, I'm just going to leave it as our, hat, not vector. I'm going to leave it as R13 for the moment, just since I run out of space. And we can talk about that as soon as I simplify that number. So because this is 0.5 squared, there's actually a bunch of 5s that cancel. That's why I chose these numbers. And so it actually works out very nicely that you get minus 45 newtons. And now we do have to worry about that. I will write it one more time. We have to worry about that R13 vector, and that's the one I have drawn along the diagonal. So the diagonal from Q1 to Q3 is our R13. So R13 vector is equal to this one, the diagonal of the 0.4, the 0.3, and we just worked out that this side would be the 0.5. I can call this theta, and then our R in my favorite column vector notation, our R hat, or yes, this one is a hat. Our R hat can be written, the cosine of theta in the x component. The x component would be the adjacent side. Go back to SOHCAHTOA, cos as the adjacent over the hypotenuse, and the sine gives me the opposite side, which is the vertical, the y component. These, I could just plug those in, minus, 45, not 4. So minus 45 newtons. I was just saying, so you can use the 4/5. The powers of 10 cancel, so I don't need to worry about the decimal points. And 3/5 for the column vector notation. 5 goes into 45 nicely and gives me a 9. So 5 into 45 gives me a negative 9, and then times 4 gives me a negative 36. And then for the x component, and then for the y component, 5 again goes into 45 and gives me negative 9. And then times 3 is negative 27. And that is in newtons, and that is F1 on 3. So now I have the two pieces. So I have F2 on 3 as a column vector, and I have F1 on 3 as a column vector. If you're taking notes while you do this, you might want to write that down. I will erase everything except for that and then rewrite it up there so that we can see everything, and then I will add them to get the final answer. going to move that up. So I have F1 on 3 equals negative 36 and negative 27 newtons. All right, so now I'm ready to go back to this version of the equation. The final answer, the force on Q3 is equal to the force of 1 on 3 vector plus the force of 2 on 3 vector, which we just worked out as column vectors. So 1 on 3 is the one I have up here, negative 36, negative 27, and then plus 0 and 100. Great thing about column vectors, why I like them so much, is that you can just add up now the rows. So the negative 36 plus 0 gives us the x component of the sum, so that's just a negative 36. And then the bottom row gives us the y components. 100 minus 27 would be 73. And it is positive. So it's the positive 100 and the negative 27, so it's positive 73, and that is newtons. So that is the answer for the force on this charge due to that one. We can sort of eyeball. The graphical solution is to put them head to toe. So you see, imagine moving this one over, and you would think that the vector goes kind of that direction, and that's exactly what we see. The x component is in the negative direction of the sum of these two force arrows that we drew, and so the net of those will be off in that direction, the negative x and the positive y, exactly what we see here.